Okay, let me explain it one more time. That we have a reconstruction filter in the end, and we have an anti-aliasing filter in the beginning. They are connected to each other in this way that if you have this anti-aliasing filter in the beginning, then the reconstruction error would be much less. So as I explained already, the structure the second structure, which uses the anti-aliasing filter in the beginning, works much better than the first one, which uses just the reconstruction filter in the end. Why? Because in the reconstruction filter, in the end, we are having a sigma over minus infinity to plus infinity. So the repetition of the baseband spectrum is happening there. If you don't have the signal cut in the beginning, what happens in the end is that you have the summation over the residuals, which are too much. And the final value would be something considerable, which corrupts the high frequency portion of the signal. But if you use the anti-aliasing filter in the beginning, which cuts the spectrum of the signal and makes it band limited, then the reconstruction happens with much less error. And the final result is much closer to the analog signal that you have in the input. So these are two filters in the beginning and the end. The reconstruction filter in the end is normally embedded inside the D2A converter. You can do nothing. It's just a chip, you buy it and you use it. But the anti-aliasing filter is something that you can have it with your design in the beginning. It's an analog filter. You can design it and you can use it in the beginning. So if you know that you can have a good number of the samples, I mean the frequency of the sampling is sufficient, you can just try a very simple anti-aliasing filter. But if you know that, for example, the sampling is very critical, so the number of the samples that you take is very much close to the bandwidth of the signal, and you're not able to guarantee the guard band to be sufficient, then here this anti-aliasing filter plays an important role. It means that you have to do something with the anti-aliasing filter to be able to have a good reconstruction in the end. Because generally you have a lot of errors during the digital processing of the signal. When you're doing any kind of processes, I'm not talking about the process at the moment. It's just the beginning and the end of the signal. I mean synthesizing of the signal in the end and analyzing of the signal in the beginning. It's just the two part of the signaling or the DSP, which is normally done for every kind of signal. So far we're just talking about that and the representation of the signal in general. But what are the processes that we have to do is something that comes with future lectures. For example, doing a kind of separation of the signal, enhancing from the noise, or dimensionality reduction, or any kind of this, or compression. These are the kind of processes that you will perform on the signal, and you don't care about the beginning and the final stage. And I'm talking about the beginning and the final stage at the moment, at least within these 2 or 3 lectures. So, the anti-aliasing filter, it has some subtleties. You can go to the book to find out what actually you can do with the anti-aliasing filter to get rid of those concerns that might happen when you don't have enough guard band. For example, at that moment, having some anti-aliasing filter, which is analog filter, I'm talking about the analog filter, to be sharp, then it's problematic. Probably you will not be able to create a kind of filter which is too sharp. Then there is a method using the oversampling, which I'll talk about the changing of the sampling rates. And then I'll come back to that solution of the anti-aliasing filter. How can we get rid of those concerns of having a sharp analog anti-aliasing filter, but you can do something that is much better than doing nothing, and you actually get a lot of gain out of that. So these are the things that we have to concern about that. Why? Because if we are not concerning about the beginning and the end, and we're just concerned about the process, we have already a lot of error in the analyzing of the signal, taking the components, and then in the reconstruction. And how we're trying to do the best process when the signal itself has already, grabbed with a lot of error, or is going to be reconstructed with a lot of error. That's the problem. So, this is the idea of how we can make an anti-aliasing filter not that much sharp, such that practically we can implement it, but it needs an oversampling here. I need to talk about the oversampling. Here is downsample. Let's see here. Is it downsampling period? This downsampling structure. I will talk about that when I come back to when I finish actually the changing the sampling rate, and then we'll talk about that in the end. So the idea, and I can say that the motivation of changing the sampling rate comes from this fact that it normally happens that someone gives you, normally if, for example, talking about the speech signal, you're recording a speech of someone as a wave file. What is that wave file that you have it? It's a sample of the speech signal. It's not the speech itself. The speech itself is an analog signal. So if you're using, for example, a kind of recorder, you already preset the recorder for a kind of sampling. You say that take the samples 44.1 kilohertz, 16 kilohertz, 8 kilohertz, based on the amount of memory that it occupies on that device. So that's the digital version of the signal, but just the name is wave. It's not a wave. It's not an analog signal. It's just a digital. Now what happens if, for example, you have 44.1 kilohertz of the signal, you have 44 recorded in the wave file, but you want to transfer these wave files to another appliance, to another device, but the problem is that the new device has 1/3 of the capacity of the original one. You don't want to cut the wave files. You don't want to ignore some of the waves. You want to have everything, all the information included. So one of the ideas is, what happens if we just take the 16 kilohertz version of that contains the entire information? Is that possible to change the sampling rate from this to this, which is called here downsampling? This idea is called downsampling. Or the other way around. For example, you have the 16 kilohertz. You want to interpolate a much better quality, for example, 96 kilohertz. What happens if you want to have 96 kilohertz? So that's the idea behind the theory of changing the sampling rates. And we know that it's not possible to ask that person that gave that speech, please take a seat here again and give the entire speech again, and I want to record it this time with 44.1 kilohertz or 16 kilohertz or 96 kilohertz. The speech is already given and it's out. And what you have is just the samples, digitized version of the samples, and you want to do something with those samples. So changing this is called the changing the sampling rate using the downsampling or upsampling. So here it's called upsampling. And we also have a ratio-based sampling. So sampling with the fraction, which is, for example, 2/3. Not necessarily 4 times or division to 4 or 3 or something. But you want to have something which is a ratio between, for example, 4/3, 3/4, or something like that. What is the idea? To do this kind of sampling, changing the sampling rates, and what happens to the signal when you have this kind of functioning over the signal? What happens? What happens to the signal in the time domain? What happens to the signal in the frequency domain? And is there anything lost or no? So that's the idea behind this changing the sampling rate. In the beginning, we're talking about downsampling. So, in general, they are represented, for example, when you say downsampling the value of n, we say x of n. In mathematics or in the DSP theory, you normally see something like this. That's the meaning of downsampling. So here, for example, you say y of n is x of mn and what this intuitively means is that, for example, if this is the signal, part of the signal, and we have samples, for example, from the signal, the signal is continuous from both sides. So there's a stream of signal coming. What happens when you say that I want to do the downsampling with the rate of 2? For example, here n equals to 2. Then what happens? It means that you need to take this sample, ignore this one, take this sample, ignore this one, take this sample, and so on. So every one sample, every other sample is ignored.
One question.
Yes.
You cannot downsample with decimals. It has to be integer.
What do you mean by decimal?
Downsample
1.5 is 3/2. So we do the upsampling and downsampling using the 3/2. So that's a ratio-based sampling. That's the the idea that comes next. But in general, what does it mean is that the output in frequency domain, the output here in the frequency domain is just, if you have n as the downsampling value, what happens in the frequency domain is just simply like this. And what does it mean in the pattern? It takes much less time if I just explain it in this part of the lecture. What does it mean? It means if you have the spaceman spectrum of the signal, this is the x e to the power of 3 omega, which is repeated every 2 pi, and we assume that there is no overlap. With the same pattern, just continue from minus infinity to plus infinity. If you have such a thing, assuming that here the magnitude of the signal in the frequency domain DTFT is 1 after doing the sampling with the ratio of m, after doing downsampling with the ratio of m. What happens? First of all, this is the new amplitude. So if this is 1, the new version should be 1 over n. The next thing here, omega over m, expansion of the spectrum, m times expansion. So if here you had omega 1 minus omega 1, for example, here you have m omega 1 minus m omega 1. And that's repeated. Assuming that, I don't know, maybe here's 2 pi, the same thing will happen. So 2 pi plus m omega 1. Here, 2 pi minus m omega 1. And the same thing continuing from this way. So, what happens? Something dangerous. What happens is that, so the spectrons probably overlap with each other. And part of the spectrum information will be lost. So assuming that, for example, if exactly you have the same spectrum like this, then when they act upon each other, you have such a thing in the end. Something like that. So we see that only part of the spectrum is remaining intact. And the rest of the information will be lost. So from this point onward, the information is lost or is corrupted. So downsampling is always subject to overlapping. The only condition that avoids overlapping is when you have m in such a way that they do not overlap. So if 2 pi minus m omega 1 is bigger than m omega 1, another way, 2 pi is bigger than 2m omega 1, or m is less than pi over omega 1, then it's possible not to have overlap. Otherwise, that will happen. So it's too dangerous. And here it's clear. Every other sample is removed. For example, you take this sample, you keep this sample, you remove this. Then you keep this sample, remove this, and so on. And if it's very smooth, it's just like this, it means that that information is located in the low frequency part of the signal. In the low frequency part of the signal. If this is a signal, here you start from the low frequencies, and here you go to the higher frequencies. From low frequencies to the higher frequencies. Low frequencies means low variation of the signal. So if here is like this, it's very smooth, you will lose nothing. You can just interpolate this and get the signal back again. But what happens if the signal variation here would be like this, and it's getting some kind of information? So if you drop the sample here, and whatever it's inside, n-1 samples in the middle, all these detailed variations of the signal which belong to the higher frequencies part of the signal, they're lost. That's why you lose the information. If you do the upsampling, downsampling with a ratio which is higher than how the signal is behaving, the details of variation of the signal. So, again, in this case, it's better to have a low-pass filter which cuts the signal from some part onward. So, if you use, for example, anti-aliasing filter in the beginning, which cuts the high frequency of the signal, then the possibility to have, here you're making the possibility to have less overlapping. So here again, it confirms that the anti-aliasing filter in the beginning is very important. So, all I said you can find in this page. I can just skip this page because everything is already mentioned. So you have a new sampling rate. Previously it was T, now you have T prime, which is different. And what you have mentioned here is completely the same. So you have the, that's called also the decimation filter. The downsampling is also called the decimation. So you see that the downsampled version of the x of n with the ratio of m is x n m. And that's the structure. So for that structure, we'd better to have, again, a low-pass filter for this entire structure. We need to have a low-pass filter in the beginning, which cuts the signal in the cutoff frequency pi over m. If you cut it with the cutoff frequency pi over m, so you're limiting the spectrum of the signal in the beginning, and it actually helps a bit after doing the overlapping. If they overlap, then the possibility of losing the information is much less. When you cut off the frequency after the pi over m, then downsampling with the ratio of m is just sticking the continuous, the adjacent spectrums to each other. But not more information than that will be lost. The other way, you will lose much more information. So, that's the structure. You already know that, and that's the entire calculations, which I wrote down the final result here, but you can find it also here. So I'll skip these 3 lectures, and I just and this is actually what happened, and I showed in this blackboard. Actually, you have the signal. When you do the downsampling, it's subject to the overlapping. But for example, in this case, if we have no overlapping, then they will just stick to each other. And there will be no information loss. Otherwise, you will have information loss. So you have the overlapping here. And when you have overlapping, so part of the information will be lost. The same idea goes for the upsampling. When you do the upsampling, so for the upsampling, you have symbolically it's written x of n. For example, you do the upsampling with the ratio of L, and you have, for example, x ln. So this x of ln can be represented as x n over L if n is KL. And that's for any other frequencies. Intuitively, what does it mean? Is that you have a kind of signal. You have already the samples like this. And you're adding samples in between. So for example, if you have the period is, for example, T. This is the period, for example, T. Then you need to have a shorter period like T prime. So you put 0 here. You're adding one sample here. So you're doing the zero padding. That's called zero padding. You add zeros between, for example, here is the ratio of when L is equal to 2, you have such a thing. You add just one sample between any two samples. And this continues. But what is the behavior in the frequency domain? This again, so simple. The frequency representation is so here from omega changing to L omega, it means that x of e to the power of j omega, here you have expansion, you have a dilation, so you have compression in the frequency spectrum. Whatever it was already in the omega spectrum is now, compressed into L omega. Very simply, the same structure for x of j omega. If you have such a thing as the spectrum of the signal, the TFT of the signal, what happens is more concentrated over the frequencies. So here you have omega 1 over L minus omega 1 over L. And the same way. So it does the opposite way as what we had in the downsampling.
Excuse me.
Yeah.
Does the amplitude looks like it might be not stopping?
No, you don't need. So, for the upsampler, we see that it's a kind of, it's like to have interpolation, but for the downsampling we had a pre-filtering. For the upsampling, normally we have a post-filter. So we use the upsampler with any ratio like L. Afterwards, we normally use a low-pass filter with a cutoff frequency of pi over L. So that's normally, it's called the interpolation. It's the other way from downsampling, which was actually decimation. Now this system is called the interpolation. It's called interpolation because it's somehow, when you do the, here the frequency, when you do the low pass filter, you know that it's like in the time domain having a sinc function. It's like to have the sinc function in the time domain. So it's just like to say that for every of these samples, I mean, everything that's, for every sample that you're adding or you're padding this between any two samples that you already have, you're actually doing a sync-based interpolation. So you have two samples, already the values are in the memory, and you're doing a kind of interpolation based on the sync function between these two. And sync function, we know that it's a smooth function. It's not a fast function or something with a high frequency. So that's a kind of interpolation. And this is different from linear interpolation. For linear interpolation, for example, if you have a value here and you value here, linear interpolation could be like this, like a line. But here is the sync-based interpolation. That's why the system is also called the interpolator. The system is also, the upsampling is called the interpolation. So it's like to say that the samples of xk, they are convolved with the sync in the time domain, which is shifted. So up and down sampling okay. We can skip through this, all of this, because the entire idea is already mentioned, and there are too many details. And if I want to go through the details, I'll not be able to talk about the rest of the things. So the general idea is mentioned already. So we have the time and the frequency correspondence between the upsampler input and output, downsampler input and output, and what happens to the spectrum. That's enough. And if we ask you, for example, the exam, that what happens, or expand the spectrum of a signal using this upsampler or the downsampler, the entire thing that we need from you is just to know the intuition behind that, and what's the relation for the frequency domain representation of inputs and outputs. Please.
I didn't understand why exactly we use post-filter in case of upsampling, because downsampling.
It's not necessary for the upsampler because nothing special happens. Normally they just use it in the upsampler. Normally they use it in the interpolator, actually, or upsampler. They use it, but it's not necessary because nothing serious happens in upsampling. Normally it's just you are somehow compressing the spectrum of the signal, and it's not dangerous. It's not dangerous, but when you are actually using upsampler and downsampler together, then that post filter of the upsampler, if the upsampler is coming first, that plays a role. Because for the upsampler you have the upsampling plus a filter, and for the downsampling you have a filter plus a downsampler. Then these two filters should be designed together. There is a consideration of designing those filters when you are having these two systems coming one after another. Just, you have two systems connected to each other. Then you have the problem. That's not the problem that always happens, but there should be some concerns in some special cases. So even we have here, for example, we are going to change the sampling rate by something non-integer. So it's a kind of like a fraction of something, m over L or something like that. Then it's completely clear that it's better to first have the upsampler than the downsampler. Why? When you're using the ratio-based sampling, it's better to have the upsampler first and then the downsampling in the next stage. For example, you want to have m over L. So you have L over m, something like that. The ratio based, something, it's not an integer value. So what should we do? Which one is should be preceded? The first one should be the downsampler or the upsampler? It should be upsampler, because downsampler you may lose the information. So it's better to first have the upsampler. That's why we use the upsampler. For example, L times upsampling here, it comes first, together with the filter, which, as I told you, is not that much critical to have this filter. But then you need to have the decimator, which cuts the frequency at pi over n and the downsampling, the final state. Then what in practice is done, these two filters are